Welcome back to the deep dive. We've had some fascinating listener submissions lately.
Oh, absolutely.
And this one, well, this research on the globular cluster M4, it couldn't have come at a better time.
Yeah, perfect timing. We were just discussing the James Webb Space Telescope and
Exactly. And guess what? This research uses JWST data to study M4's white dwarfs.
it really is giving us a whole new perspective.
For sure.
Sure.
Just a quick refresher for everyone listening. Globular clusters, they're like these massive swarms of stars among the oldest in the universe.
Yeah, think ancient, dense, packed with stellar history.
Right. And L4, it's a particularly interesting one.
It is, sitting about 1.85 kiloparsecs away. That's over 6,000 light years. And it has a metallicity of you. Ready for this? FeH equals 1.18.
Okay, I'm taking notes. Now, you mentioned the James Webb Space Telescope. What makes it so groundbreaking for studying M4?
Well, its infrared vision is key here. Because it allows us to see through the dust and gas that usually obscures these clusters. It's like we finally got the right tool for the job.
It's like we've been given X-ray vision. That's got to be crucial for M4, right? Especially since it's in a pretty dusty region in the sky.
Absolutely. M4 lies in an area with a lot of interstellar dust. But the JWST cuts right through it, giving us a clear view of those white dwarfs.
Okay, so we're talking white dwarfs. These are what, the retirement homes for stars like our sun.
Exactly. The afterlife, if you will.
I love that. And I'm guessing this ties into the whole cosmic clock concept.
Got it. As white dwarfs cool, they fade. And this fading, this cooling process, it happens in a predictable way, like a clock ticking down.
So we can use that to, estimate the age of these star clusters.
Precisely. And in fact, previous studies using Hubble, the Hubble Space Telescope,
Of course.
they estimated M4 to be somewhere between 11.6 and 12.1 billion years old, based on this white dwarf cooling sequence.
Okay, so that was Hubble. But now we have the JWST and its infrared observations. What's this new research revealing about M4's age?
Well, they've been able to pinpoint the peak of the white dwarf luminosity function using JWST data. Basically, that means they figured out the brightness level where you find the most white dwarfs in M4.
So more white dwarfs at a specific brightness equals a clue to the cluster's age.
Exactly. Combine that with the distance to M4 and how much dust is in the way, and you get a refined age estimate.
Drumroll, please. How old is M4?
The data suggests about 12.2 billion years old.
Wow. Almost as old as the universe itself. Now, they didn't stop there, right? They compared M4's age to another famous cluster.
You're thinking of NGC 6397?
Yeah.
Another well-studied globular cluster?
Yes, a cosmic age comparison. So which cluster wins the oldest award?
Actually, it seems M4 is slightly younger than NGC 6397.
Really?
Yeah, by about 0.8 billion years, give or take 0.5 billion years, of course. So NGC 6397 clocks in at roughly 13 billion years old.
Wow, that's ancient. But this age difference, even if it's small, it's got to have some implications, right?
Absolutely. Globular clusters, we think they formed early on in the universe. But the details of their formation, how they evolve, still a puzzle.
And comparing the ages of different clusters like this, that helps us fill in the gaps.
It helps us refine those models, yeah, and understand the early universe better.
Each cluster, like a piece of a giant cosmic jigsaw puzzle.
I like that. And here's something else. M4 is in a pretty crowded region of space.
Yeah, you mentioned that earlier.
Right, but it's still younger than NGC 6397, which is in a less dense area. That makes you wonder, right? Does the environment affect how a cluster evolves?
Intriguing. So it's not just age. It's also about the journey of the environment each cluster has gone through over billions of years.
Exactly. Now, remember that red excess you mentioned earlier around some of the white dwarfs?
Oh, yeah. That's where things get really interesting.
It could be a sign of something truly unexpected.
Unexpected like what? Come on, spill the beans.
Well, we'll dive deeper after the break, but what if this red excess hints at the remnants of ancient planetary systems?
Ancient planetary systems, orbiting these white dwarfs in the heart of a globular cluster.
That's the question, isn't it? Stay with us.
We'll be right back after a short break.
So this red excess, it's like this, a faint infrared glow around some of M4's white dwarfs.
Okay, debris disks. Help me picture this. What are we talking about exactly?
All right, imagine a planetary system, kind of like ours, but billions of years older. The star has gone through its life cycle, ended up as a white dwarf.
Right, the retirement home.
Exactly.
Yeah.
Now, some planets, they might survive all that, but others, they get disrupted, maybe even destroyed. during that red giant
Oh,
phase.
wow. It's like a cosmic demolition derby. So what happens to, the leftovers?
That's where these debris disks come in. All that disrupted material, dust and gas, it forms a disk around the white dwarf. And that disk, it could be what's giving off that extra infrared light, the red excess.
Okay, so it's like a faint, dusty halo around the white dwarf, glowing in infrared, and it might be, what, a graveyard of planets. That's incredible. You mentioned debris disks have found around other white dwarfs in the Milky Way. What makes this potential discovery in M4 so special?
It's the environment. Globular clusters, they're ancient and incredibly dense. Those stars, packed in so tightly, way stronger gravitational interactions than, say, in our galactic neighborhood.
It's like a mosh pit of stars.
Exactly. Now imagine planets forming in that environment. It wouldn't be a peaceful existence, would it? Like our solar system?
No, definitely not. Constantly getting tugged on by all those nearby stars.
Right. So the possibility of finding evidence of planetary systems in M4, in a globular cluster, that's huge. It would mean planet formation is tougher than we thought, able to withstand even these crazy conditions.
It's like finding a delicate flower growing in a war zone. Mind-blowing. Now, I know there's another possible explanation for this red excess. What about companion stars?
Ah, yes. Good point. We are dealing with faint signals here. So it's possible we're not looking at just one white dwarf, but a binary system.
Like a white dwarf with a little friend, a smaller, dimmer star.
Exactly. Imagine a white dwarf hanging out with a small, cool red dwarf star.
Red dwarf.
Now, red dwarfs, way fainter than white dwarfs in visible light, but in infrared, they can be quite bright.
I see where you're going with this.
So if you've got this binary pair, their combined light would look redder than just the white dwarf alone. And that could be what we're seeing as the red excess.
Oh, okay, so it could be a trick of the light. We think it's one white dwarf with a debris disk, but it's actually two stars snuggled up, blending their light together. How do we solve this cosmic mystery? How do we tell the difference between a debris disk and a companion star?
That's where we need to get even more detailed. We need spectroscopy, analyzing the spectrum of light from these systems, looking for those telltale signs.
We're looking for what, like fingerprints in the light?
Exactly. Debris disks, they often show emission lines from specific elements. That's the dust and gas talking.
And companion stars.
They'll have a more continuous spectrum, like other stars. And I've heard the researchers are planning more observations of M4 with JWST, but this time, maybe using longer wavelengths, possibly even MERI, the mid-infrared instrument.
Oh, MIRI. Now that's an instrument I've heard great things about. Isn't that designed specifically for the mid-infrared?
It is, and that's perfect for studying cooler objects, like debris disks. You see, MIRI can detect the fainter, longer wavelengths that NIRCam, the instrument they used in this study, might miss.
It's like we're getting a more powerful magnifying glass to get a better look at those potential dusty halos. What could MIRI reveal about these disks?
Well, we could learn a lot more about their composition, how they're structured, maybe even pinpoint specific minerals or molecules in that dust.
So it's like cosmic archaeology, trying to reconstruct what was there billions of years ago. Amazing. Now, you mentioned before that this research could change how we think about planet formation. Can you expand on that a bit?
Sure. We usually think of planet formation happening early on, right, around young stars. But if we find these debris disks around white dwarfs in M4, it would mean planets can form much later in a star's life.
It's like saying there's not just one window of opportunity for planets to form.
Exactly. It's possible there's a whole other way for planets to form, billions of years after the star has moved off the main sequence. And remember, we're talking about a chaotic, rough environment here.
So planets could form later, and in places we thought were too hostile.
Precisely. It really broadens our understanding of where and when planets can form.
Wow. I'm having to rethink everything I thought I knew about planetary systems. But let's not get ahead of ourselves. These are still possibilities, right?
Right. We need more observations to be absolutely sure these debris disks are really there.
Okay, back to reality. So what's next? What other researcher observations could really nail this down? Welcome back to the deep dive. I'm still kind of reeling from all that. Ancient planets, white dwarfs, globular clusters. It's a lot to take in.
It really is. It makes you realize just how much we still don't know about the universe and, planet formation. It's pretty humbling, actually.
Totally agree. So, okay, we're talking about the possibility of debris disks around these white dwarfs. What kind of observations would, definitively confirm that? Really nail it down?
Well, more spectroscopy. Remember how we were talking about those emission lines? Each element, it emits light at specific wavelengths, right? It's like a fingerprint.
Right, those cosmic fingerprints.
Exactly. So if we can analyze the light from these white dwarfs even more closely, look for specific emissions that tell us, hey, there's dust and gas here, that would be huge.
So it's like a cosmic detective story. We're analyzing the evidence, the light, to figure out what was going on billions of years ago. I love it.
And you know what? The JWST has the perfect tool for the job. MIRI, the mid-infrared instrument.
MRI. I feel like we should be playing dramatic music when we say that. It sounds so powerful.
Well, it kind of is. Think about it. Different wavelengths of light, they show us different things. MIRI is designed to observe in the mid-infrared, where cooler objects like dust grains, they really shine.
Oh, I see. So it's like we're switching to a thermal camera.
Yeah.
Suddenly we can see things that were invisible before.
Exactly. That's a great way to put it. With MIRI, we could potentially map out the temperature inside these debris disks, figure out how big they are, how dense they are. We might even be able to identify what that dust is made of.
Wow. It's like we're on the brink of unlocking some incredible secrets. Now, I want to go back to something we talked about earlier, the age difference between M4 and that other cluster, NGC 6397.
Yeah, M4 being slightly younger.
Right. What does that tell us, about how globular clusters form and evolve?
Well, the traditional idea is that these clusters, they formed early in the universe in a quick burst of star formation, like boom, all at once.
So all the stars in a cluster should be roughly the same age.
That's the classic picture. But lately, we've been seeing hints that it might not be that simple. Like with M4, there are these little age differences popping up. Maybe there are multiple bursts of star formation, or maybe smaller clusters merged together.
So maybe it's not a simple born together, die together story for these clusters.
Right. And even that small age difference between M4 and NGC 6397, it could mean that different clusters, they went through slightly different evolutionary paths.
It's amazing to think about, these tiny, faint white dwarfs. They're telling us these epic stories about the history of our galaxy.
It really shows you the power of science, of observation, of asking questions. We're learning so much about how galaxies form and evolve just by studying these stellar remnants.
And with JWST, it feels like we're just getting started. Who knows what other mysteries are out there, hidden in the light of those ancient stars?
That's what makes it so exciting. There's always more to discover, more to learn.
Absolutely. Well, I think we've reached the end of our deep dive into M4 and its fascinating white dwarf population. We've covered a lot of ground: stellar evolution, ancient planetary systems, the vastness of cosmic time.
It's been quite a journey. I hope everyone listening enjoyed it.
Me too.
Yeah.
It's been a pleasure chatting with you as always. And to everyone listening, thanks for joining us on the deep dive. Keep looking up at those stars, and we'll be back soon with another deep dive into the mysteries of the universe.